Look at your screen. You're reading this right now. Why? Because the screen is bombarding you with photons, trillions of them, every second, hitting your retina, being absorbed, creating electrical signals that your brain interprets as text. Without those photons, the screen wouldn't exist for you. Wouldn't be visible. Wouldn't exist. Period. Everything you see exists because it's exchanging photons with you right now. Your hands, the walls, the furniture. Every object is either emitting photons or reflecting them toward you. Active exchange. No photons, no reality. The universe becomes invisible instantly. Not dark, not black. Invisible. Non-existent from your perspective. Gone. Now, we usually think objects are just there. They exist whether we look at them or not. And we see them passively. Light bounces off, enters our eyes, and we perceive. Simple story. That's not wrong, exactly. But it's misleading. Seeing is an active process, an exchange. Objects emit or reflect photons. Those photons travel through space. They hit your retina absorbs them. That absorption creates chemical changes. Those changes create electrical signals. Your brain interprets those signals. Every step involves interaction. And here's the key thing. The thing that quantum mechanics tells us, and this might bother you, without that exchange, the object doesn't exist for you. Not in any meaningful sense. Not really. In quantum mechanics, observation isn't passive. Observation is interaction. And interaction requires photons. Has to. Let me tell you what a photon actually is. What's really going on. A photon is a quantum of electromagnetic force. A particle. But also a wave. It's both, depending on how you measure it. Weird, but that's nature. But more importantly, photons are messenger particles. They mediate the electromagnetic force. Carry it between things. When two electrons repel each other, how do they do it? They exchange photons. Virtual photons, we call them. Photons that exist for a tiny fraction of a second. Just long enough to carry the force between the electrons. Blink, and they're gone. Richard Feynman developed diagrams to visualize this. Feynman Diagrams. Two electrons approach. One emits a virtual photon, the other absorbs it. Momentum transfers. The electrons repel. Beautiful. The photon is the messenger, the carrier of the electromagnetic interaction. Now, virtual photons are different from real photons. Real photons are the ones you can see, light. They can travel forever, in principle. Virtual photons exist briefly, then disappear. But they're both photons, both quanta of the electromagnetic field. When you see an object, you're detecting real photons, photons that were emitted or reflected by the object. Here's how it works. Light from the sun or a lamp hits the object. The photons in that light have energy. When they hit atoms in the object, they interact with electrons. Bang. The electrons absorb the photons. The energy excites the electrons to higher energy states. Then the electrons drop back down and re-emit photons in all directions. Some of those photons travel toward your eye, enter your pupil, hit your retina, get absorbed by molecules in your retina, and the process of vision begins. But here's the thing, and pay attention. The photons your eye receives aren't the original photons from the sun or lamp. They're new photons, emitted by the object. The object absorbed incoming photons and re-emitted new ones. That's what reflection really is. Absorption and re-emission. Not bouncing like a ball off a wall. Creation and annihilation. Now, the color you see depends on which photons the object re-emits. A red apple absorbs most photons except red ones. It re-emits red photons, preferentially. Those are the ones that reach your eye. Your brain interprets that as red. But color isn't a property of the apple. Color is a property of the photons, specifically their energy. Red photons have lower energy, about 1.8 electron volts. Blue photons have higher energy, about 3 electron volts. When you see red, your retina is being hit by low energy photons. When you see blue, high energy photons. The apple doesn't have color. The apple interacts with light in a way that results in certain photons being re-emitted. Your eye detects those photons. Your brain creates the sensation of color. Feynman said this clearly. Without photons, there's no vision. Without vision, there's no observable reality. Now, let's talk about black objects. Why do they look black? Because they absorb almost all photons. They don't re-emit many in the visible range. Very few photons reach your eye from a black object. Your brain interprets that lack of photons as black. But black isn't a color, really. It's the absence of visible light. Black objects still emit photons, by the way. Infrared photons. Thermal radiation. Everything above absolute zero emits thermal photons. But your eyes can't see infrared, so the object looks black to you, even though it's glowing in infrared. If you had infrared vision, black objects wouldn't look black, they'd glow. Some animals can actually see this. Pit vipers, for instance. They detect infrared from warm prey in complete darkness. Now, transparent objects. Why can you see through glass? Because photons pass through without being absorbed. The energy of visible photons isn't right to excite electrons in glass. Wrong frequency. So the photons travel through. They don't get absorbed and re-emitted. If they did get absorbed, the glass would be opaque, but they don't, so you can see through. Ultraviolet photons, on the other hand, do get absorbed by glass. Glass is opaque to UV. That's why you can't get a suntan through a window. The UV photons that cause tanning are blocked. Different photon energies interact differently with different materials. That's what determines transparency, opacity, color, all of it. Here's something interesting. Phosphorescent materials, glow-in-the-dark stuff. You expose it to light during the day, it absorbs photons, the electrons get excited to high energy states, but instead of dropping back down immediately, they get trapped in metastable states. Slowly, over hours, the electrons drop back down. Each time one drops, it emits a photon. That's the glow you see at night. The material is re-emitting photons it absorbed earlier. Delayed emission. Now let me tell you something you might not realize, and this is fun. You emit photons. Right now. Constantly. You're glowing. Your body is warm. About 37 degrees Celsius. At that temperature, you emit about 100 watts of thermal radiation, infrared photons. You're glowing. Literally. You're a light source. You just can't see it because the photons are infrared, but thermal cameras can see it. When you see a thermal image, you're seeing infrared photons that were emitted by warm objects, including you. You are literally a source of light, real photons. Every object around you is doing the same, emitting thermal photons. The hotter the object, the more photons it emits. Very hot objects emit visible light. A piece of metal heated to 700 degrees glows red. That's thermal radiation shifting into the visible spectrum. Heat it more, it glows orange, then yellow, then white. The photon energy is increasing as temperature increases. The sun glows because it's hot, about 5,800 degrees at the surface. At that temperature, it emits photons across the entire visible spectrum. That's why sunlight looks white. So emission and reflection, those are the two ways objects send photons to your eye. And without those photons, the objects don't exist for you. Now, here's where it gets deep. Observable reality is made of photons. When you look around, everything you see is a pattern of photons hitting your retina. Different intensities, different energies, different timing. Your brain constructs a model of the world from that pattern. But the world you experience is the model, not the underlying reality. The model is built from photons. If the photon flux stops, the object disappears from your model. It ceases to exist in your observable reality. Does the object still exist objectively? Maybe, probably. But you can't know. You can't interact with it without photons. In quantum mechanics, this becomes profound. What does it mean for something to exist if you can't interact with it? There's a famous question. If a tree falls in the forest and no one is around, does it make a sound? The answer depends on what you mean by sound. If you mean pressure waves in air, yes. Those happen whether anyone hears them or not. But if you mean the sensation of sound, the experience, then no. Sound requires a listener. Same with photons and vision. Objects might emit photons even if no one sees them. But the experience of seeing the observable reality requires detection, absorption, interaction. Colors don't exist without photons, not in any meaningful sense. Color is your brain's interpretation of photon energies. No photons, no colors, just nothing. You are being bombarded by trillions of photons every second, from every direction. Reflected sunlight, lamplight, thermal radiation, a constant barrage. Each photon carries information, energy, direction, polarization. Your retina absorbs a tiny fraction of them. And from that tiny sample, your brain reconstructs the world, fills in gaps, makes assumptions, creates the seamless visual experience you have right now. But it's all based on photons, discrete particles of light hitting discrete molecules in your retina. Now, in quantum mechanics, observation has consequences, real consequences. You can't observe something without interacting with it. And interaction changes the system, always. The famous double-slit experiment. Electrons pass through two slits. They create an interference pattern. They're behaving like waves. But if you try to observe which slit the electron goes through, the interference pattern disappears. Why? Because observing requires photons. You have to bounce photons off the electron to see where it is. And when a photon hits an electron, it transfers momentum. It changes the electron's trajectory. The act of observation disturbs the system. You can't observe without interacting. And you can't interact without photons, at least not electromagnetically. I said photons are the interface between you and reality. That's a profound statement. Everything you know about the world comes through photons or other particles, but mostly photons for vision. Your entire visual experience is mediated by photons, trillions of them, every second, creating patterns in your retina that your brain interprets as the world. Here's something else. Photons don't just allow you to see the universe, they make it observable. And in quantum mechanics, observable is the only thing that exists in a practical sense. An electron in an atom is in a superposition of states, multiple energy levels at once. Until you measure it, until a photon interacts with it, then it collapses to a definite state. The photon doesn't just reveal the state, it creates the state. The interaction is what makes the electron's energy definite. Before the photon, the electron was in limbo, a blur of possibilities. After the photon, it's in a specific state. Observable, real. That's why I said photons create reality. Not just allow you to see it, actually create the observable reality. Big difference. Now, I'm simplifying. There's a lot of subtlety here. Decoherence, measurement, interpretation of quantum mechanics. People argue about this endlessly. Physicists love to make simple things complicated. It's in our DNA. We take something beautiful like light lets you see and turn it into photon-mediated quantum state collapse via observer-dependent wave function reduction. See? We can't help ourselves. But the basic point stands. Photons are how you interact with the electromagnetic world. And that's most of what you see. Let me tell you about photon statistics. When you look at a dim object, your retina isn't receiving a continuous stream of light. It's receiving individual photons, one at a time, randomly. At very low light levels, you can actually perceive the randomness, the graininess. That's individual photons hitting individual receptors. Your eye is sensitive enough to detect single photons, in principle, though in practice you need several to trigger a signal. You're detecting individual quanta of light, particles, not waves, discrete packets of energy, and each photon is either absorbed or it's not. Binary, quantum. That's the quantum nature of light, and it's detectable with your own eyes. You can see quantum mechanics. Now, here's something that connects to relativity. Photons have no mass. They always travel at the speed of light. They can't go slower. They can't stop. From the photon's perspective, if it had one, no time passes. The photon's journey from emission to absorption takes 0 time in its own reference frame. So when a photon leaves the sun and hits your eye, 8 minutes pass from your perspective. But for the photon, 0 time. It was emitted and absorbed simultaneously. The photon connects events across space and time. It links the sun 8 minutes ago to your retina now. But from the photon's perspective, those events are the same event. No separation in time. Photons are timeless messengers. They carry information from the past to the present, but they experience neither past nor present. Strange, isn't it? That the particles that create your entire visual reality, that mediate all electromagnetic interactions, don't experience time at all. Now, let's talk about the sheer number of photons. How many are hitting you right now? In bright sunlight, about 10 to the 17th photons per square centimeter per second. That's 100 million billion photons per square centimeter per second. Look, it's such a ridiculously big number that if you tried to count them one by one, the universe would end before you got halfway through. The heat death of the cosmos would happen, stars would burn out, galaxies would drift apart, and you'd still be counting. So don't try. Just accept that it's a lot. Physicists love throwing around numbers like this to sound impressive. Trust me, we know it's absurd. Your retina is about 6 square centimeters. So in sunlight, about 6 times 10 to the 17th photons per second hits your retina. Most of them aren't absorbed. Your retina is selective. But still, billions of photons per second are being absorbed, creating signals, generating the image you see. Indoors, with artificial light, the number is lower. Still trillions. Even in dim light, you're being hit by billions of photons per second. Never stops. And every single one of those photons carries information. Your visual system extracts that information, processes it, builds a model. That's what vision is. Processing photon statistics to infer the state of the world. You're not seeing objects directly. You're seeing the pattern of photons they emit or reflect. And from that pattern you infer shape, color, distance, motion. It's indirect, mediated, but incredibly effective. Now, there's a subtlety about reflection. I said objects absorb and re-emit photons. But at the quantum level, it's more complicated. When a photon interacts with an atom, the photon is annihilated. The energy is absorbed by an electron. The electron jumps to a higher energy state. Then the electron drops back down. A new photon is created, emitted. So the photon you see isn't the original photon. It's a new photon, created by the atom. Does that matter? Philosophically, maybe. Practically, no. The information is what matters, but it's worth knowing. The photon you detect isn't the photon that left the sun. It's a descendant. Created by an atom in the object you're looking at, the original photon is gone, annihilated. Its energy transferred through a chain of absorptions and emissions until a new photon reaches your eye. That new photon is then annihilated in your retina. Its energy transferred to a molecule. That molecule changes shape, triggers a cascade, generates a nerve signal, energy flowing through the system, photons being created and destroyed at every step. But the information persists. Here's another thing. Photons have momentum. Not much, because they have no mass. But they have momentum proportional to their energy. When a photon hits an object, it transfers that momentum. The object recoils, tiny amount, usually undetectable. But it's there. Solar sails use this, large reflective sails in space. Photons from the sun hit the sail, transfer momentum. The spacecraft accelerates, pushed by light, slowly, very slowly. But it works. You can propel a spacecraft with sunlight, with photons. Radiation pressure, it's called. It's tiny. But over time, it adds up. So photons aren't just messengers. They carry momentum. They can push things. In a sense, when you see something, photons from that object are pushing on your retina infinitesimally. But they are. Vision involves physical contact, mediated by photons. Now, let me tell you something about light and chemistry. Photosynthesis, the process that powers most life on Earth. Plants absorb photons. The photons excite electrons in chlorophyll molecules. Those excited electrons drive chemical reactions. Sugar is synthesized. Oxygen is released. All powered by photons. The energy of sunlight, captured in chemical bonds. That energy eventually powers you. When you eat plants, or animals that ate plants. So photons aren't just how you see the world. They're how energy from the sun reaches you, how life is sustained. Every calorie of energy you use came from photons, ultimately. Absorbed by plants, stored in chemical bonds, transferred through the food chain. You are, in a very real sense, made of sunlight. Photons captured by plants, converted to matter, eaten by you. The energy in your body is photon energy, transformed. You're walking sunlight. Now back to observation and reality. In quantum mechanics, the observer effect is fundamental. You can't measure something without affecting it. Why? Because measurement requires interaction. And interaction transfers energy and momentum, changes the system. For photons, this is obvious. You see an electron by bouncing a photon off it. The photon hits the electron, momentum transfers. The electron's trajectory changes. If you use lower energy photons, you disturb it less. But then your measurement is less precise. If you use higher energy photons, you can locate it precisely, but you disturb it more. There's a trade-off. Precision versus disturbance. Heisenberg's uncertainty principle. Can't beat it. And it's all mediated by photons, the particles you use to observe the quantum world. So photons aren't neutral. They're not passive. Observation with photons changes the system, always. That's why I said photons create observable reality. The act of observing, of interacting with photons, is what makes things definite, real, observable. Without that interaction, things are in superposition. Undefined, potential, not actual. The photon interaction collapses the wave function, makes the system definite, observable, and that's the only reality you can access. The reality created by interaction, mediated by photons. Now, does this mean reality doesn't exist without observers? That's a deep question. Philosophers and physicists argue about it, have been for decades. Some say yes. Reality is created by observation. Without observers, there's just potential. Others say no. Reality exists independently. Observation just reveals it. I don't know the answer. Nobody does. It's interpretation. Philosophy more than physics. But what's clear is this. Your reality, the world you experience, is created by photons. Without them, you have no access to the visual world. Nothing. That's roughly where we are. Photons are the interface, the mediator, the messenger. They carry information from objects to your eyes. They allow you to see, to observe, to know. But they also change what they observe. They interact. They disturb. They create definite states where before there were only probabilities. Every object you see exists because it's exchanging photons with you right now. Trillions per second. Creating patterns in your retina. Patterns your brain interprets as reality. Without those photons, the object doesn't exist for you. It's not observable, not knowable, not part of your reality. When you look at your screen, you're capturing photons it's emitting right now. This instant. The screen is bombarding you constantly. If the photons stopped, the screen would vanish. Not go dark. Vanish. Cease to exist in your observable universe. Poof. Photons don't just let you see the universe. They make it observable. And in quantum mechanics, observable is the only thing that exists in a meaningful way. Photons don't reflect reality. They create it. Interesting, isn't it? Now you know what you're really seeing. Photon patterns. That's it. That's all it ever was.